You've heard this statistic before. We've explored less than 5% of Earth's oceans. It gets thrown around constantly, usually followed by, we know more about the surface of Mars than our own ocean floor. But have you ever stopped to wonder if that's actually true? And more importantly, why is it true? Because here's the thing. We've sent humans to the moon. We've landed rovers on Mars. We've photographed black holes 55 million light years away. We have the technology to split atoms and edit genes. So why can't we just look at the ocean floor? The answer is way more complicated and interesting than you think, and it reveals something fascinating about the limitations of human exploration and technology. Let's dive in, literally. Part 1. What does 5% explored actually mean? First, we need to get our facts straight because that 5% number is actually misleading in multiple ways. When people say we've only explored 5% of the ocean, they're usually talking about high-resolution mapping of the seafloor. But here's what they don't tell you. We've actually mapped about 20 to 25% of the ocean floor to a decent resolution as of 2024. The rest, we've got rough data, but nothing detailed. Think of it like this. Imagine you're trying to map a city. We've done the equivalent of satellite photos for most of the ocean. We can see major features, but we can't read street signs or see individual buildings. For about 20% of the ocean, we've got street-level detail. For the rest, we're still looking at blurry satellite images. But mapping is just one aspect of exploration. When we talk about exploring the ocean, we could mean mapping the seafloor topography, understanding the geology and chemistry, cataloging marine life, studying ocean currents and temperatures, discovering shipwrecks and archaeological sites, understanding deep-sea ecosystems. By some of these metrics, we've barely scratched the surface. We've probably discovered less than 10% of marine species. We don't fully understand the complex circulation patterns of deep ocean currents. There are vast regions where humans have never been, where no submarine has ever descended, where no camera has ever recorded footage. So yes, the ocean is genuinely unexplored in meaningful ways. But why? Part 2. The ocean is trying to kill you. Here's the fundamental problem. The ocean is one of the most hostile environments imaginable for humans and our technology. Let's start with pressure. At sea level, atmospheric pressure is about 14.7 pounds per square inch. That's the weight of all the air above you pressing down. Doesn't sound like much, right? Now go 10 meters underwater. The pressure doubles. You've got the atmosphere above you, plus the weight of 10 meters of water. Go to 100 meters. That's about 328 feet, roughly the length of a football field. And you're dealing with 10 atmospheres of pressure. The average depth of the ocean is about 3,688 meters, or roughly 12,100 feet. At that depth, the pressure is about 370 times atmospheric pressure. That's 5,400 pounds per square inch. Imagine having nearly 3 tons of weight pressing on every square inch of your body. Your lungs would collapse instantly. Your bones would shatter. You'd be crushed like a soda can in a hydraulic press. But it gets worse. The deepest part of the ocean, the Challenger Deep, in the Mariana Trench, is about 11,000 meters down, or 36,000 feet. The pressure there is over 1,000 atmospheres. That's 16,000 pounds per square inch, 8 tons per square inch, the weight of 50 jumbo jets pressing on an area the size of your thumbnail. At those pressures, things behave weirdly. Water becomes slightly more dense. Gases dissolve into strange states. Most materials we build things from simply can't withstand the force. Steel deforms, glass cracks, even specialized titanium alloys struggle. Compare this to space exploration. In space, you're dealing with zero pressure, a vacuum. You need to keep pressure in your spacecraft to keep humans alive. That's actually easier than keeping crushing pressure out. A spacesuit needs to maintain 1 atmosphere inside against 0 outside. A deep-sea suit needs to maintain 1 atmosphere inside against hundreds or thousands outside. The engineering challenges are completely different and, in many ways, harder for the ocean. And it's not just pressure. The temperature at the ocean floor is typically between 0 and 3 degrees Celsius, just above freezing. Your equipment needs to function in near-freezing temperatures while simultaneously withstanding crushing pressure. Electronics behave differently in these conditions. Batteries drain faster, lubricants freeze or become viscous, seals become brittle. Then there's corrosion. Seawater is incredibly corrosive, especially at depth where the chemical composition changes. Salt water attacks metals, degrades seals, and damages sensitive equipment. Materials that work perfectly fine on land or in space can fail rapidly in the ocean environment. Part 3. You can't see anything down there. Pressure isn't the only problem. The ocean is dark. Really, really dark. Sunlight penetrates seawater to varying degrees depending on wavelength. Red light is absorbed within the first 10 meters. Orange goes a bit deeper. Yellow makes it to maybe 30 meters. By the time you're 200 meters down, just 600 feet, which is nothing in ocean terms, you're in complete darkness. This zone is called the aphotic zone, meaning without light. It comprises about 90% of the ocean's volume. It's permanently, absolutely dark. No sunlight has reached these depths in billions of years, since the ocean formed. So if you want to explore the deep ocean, you need to bring your own light. But light doesn't travel far in water. Even with powerful lights, you can only illuminate a small area around you. It's like trying to explore a massive warehouse with a flashlight. You can see what's right in front of you, but the vast darkness surrounds you on all sides. This makes comprehensive surveying incredibly difficult. On land, we can use satellite imagery to photograph entire continents. In space, we can point telescopes and see galaxies billions of light years away. But in the ocean, we're limited to what we can illuminate with artificial light in a tiny sphere around our instruments. Visibility in seawater is also affected by particles suspended in the water, organic matter, sediment, plankton. In some areas, visibility might be only a few meters even with bright lights. It's like trying to explore during a foggy night. Your lights just reflect off the particles and create a murky haze. Part 4. Water blocks all our best sensors. Here's where it gets really frustrating. Water blocks electromagnetic radiation. Radio waves, which we use for communication and radar, absorbed by seawater within meters. GPS signals don't penetrate water at all. Satellite communications, useless once you're submerged. This means submarines and deep-sea vehicles are essentially cut off from the outside world. They can't receive GPS signals to know where they are. They can't communicate with the surface except through acoustic signals, sound waves, which travel slowly and have limited bandwidth. On Mars, rovers can send high-resolution images and data back to Earth via radio. In the ocean, sending even simple messages from the deep sea floor to a ship on the surface is complicated and slow. We use sonar, sound waves, to map the ocean floor and navigate underwater. But sonar has significant limitations. It can give you a general picture of the topography, but the resolution is limited compared to what we can achieve with electromagnetic sensors on land or in space. High-frequency sonar provides better resolution, but doesn't travel as far. Low-frequency sonar travels farther, but gives blurrier images. You're always making trade-offs. Compare this to mapping land or other planets. We can use LiDAR, light-based radar, synthetic aperture radar, photogrammetry, multispectral imaging, and dozens of other remote sensing techniques that rely on electromagnetic radiation. None of these work effectively underwater. This fundamental limitation means we can't map the ocean floor from satellites the way we can map Mars or the Moon. We need to send ships equipped with sonar to physically traverse the area, mapping it bit by bit, which is slow and expensive. Navigation underwater is also challenging without GPS. Submarines and ROVs use inertial navigation systems, which track position based on accelerometers and gyroscopes. But these drift over time, accumulating errors. They need to be recalibrated periodically, using acoustic beacons or by surfacing. Part 5. It's really expensive. Let's talk money, because ocean exploration is obscenely expensive. Building a submarine, or ROV, remotely operated vehicle, capable of reaching the deep ocean costs tens to hundreds of millions of dollars. The materials need to withstand enormous pressure. The systems need to work in darkness, cold, and isolation. Everything needs redundancy, because if something breaks at 10,000 meters depth, you can't exactly call for a repair truck. The deep-sea Challenger submarine that James Cameron used to reach the Challenger Deep cost about $8 million to build. That was for a relatively small, one-person vehicle designed for a single mission profile. Larger, more capable submarines cost far more. Operating these vehicles is also expensive. A single deep-sea expedition can cost millions of dollars. You need a specialized research vessel that costs $30,000 to $50,000 per day to operate, a submarine or ROV with operating costs of thousands per dive, a crew of highly trained specialists, pilots, engineers, scientists, sophisticated equipment for sampling, imaging and data collection, months of planning and logistics, support infrastructure, including maintenance facilities. For context, James Cameron's solo dive to the Challenger Deep in 2012, including development of the submarine and the expedition itself, cost an estimated $8 million total. That was for one person to spend a few hours at the bottom of the ocean. Compare this to space exploration, which gets far more funding. NASA's annual budget is over $25 billion. NOAA, the National Oceanic and Atmospheric Administration, which handles ocean research, gets less than $7 billion annually, and only a small fraction of that goes to ocean exploration specifically. Why the disparity? Partly because space exploration captures public imagination more than ocean exploration. Partly because space has more obvious strategic and commercial value. Satellites for communication and navigation, potential asteroid mining, national prestige. Partly because we've culturally decided as a society that looking outward to the stars is more exciting than looking downward into the abyss. But the result is that ocean exploration gets a tiny fraction of the funding that space exploration receives, which means progress is slow. There's also less commercial incentive. While there are resources in the ocean, fish, oil, minerals, most are accessible at shallower depths or can be exploited without deep exploration. Deep-sea mining is theoretically valuable, but faces technical challenges and environmental concerns. There's no ocean equivalent of the lucrative satellite industry, driving private investment. Part 6. The ocean is absolutely massive. Let's talk scale, because people fundamentally don't appreciate how big the ocean actually is. The ocean covers 71% of Earth's surface. That's 361 million square kilometers, or about 139 million square miles. For comparison, the entire land area of Earth is only 149 million square kilometers. The Pacific Ocean alone is larger than all land area combined, but surface area doesn't tell the full story. The ocean has depth. The average depth is 3,688 meters, over 2 miles. The total volume of the ocean is about 1.335 billion cubic kilometers. That's 1,335,000,000 cubic kilometers of water. To put that in perspective, if you wanted to explore every cubic kilometer of the ocean, spending just 1 hour in each, it would take you over 152,000 years of continuous exploration. And that's just for a cursory visit to each cubic kilometer, not a thorough examination. Even mapping the ocean floor is a monumental task. We've mapped 100% of Mars's surface to a resolution of about 100 meters per pixel or better. We've mapped the moon's surface in even greater detail. Venus, despite its thick atmosphere, has been mapped by radar from orbit. But for Earth's ocean floor, we've only mapped about 20 to 25% to a comparable resolution of 100 meters. The rest has been mapped to much lower resolution, maybe 1 to 5 kilometers per pixel, using satellite altimetry, which measures tiny bumps in the ocean surface caused by gravitational variations from underwater mountains and trenches. Why is mapping other planets easier than mapping our own ocean floor? Because we can use radar and other electromagnetic remote sensing from orbit. For the ocean, we need to send ships equipped with multi-beam sonar to physically traverse the area, mapping it piece by piece. A modern research vessel with state-of-the-art multi-beam sonar can map a swath of ocean floor about 4 to 6 times the water depth as it travels. In deep water, say 4,000 meters, that's a strip about 16 to 24 kilometers wide. Sounds good, right? But the ship travels at maybe 10 to 12 knots, covering roughly 200 to 300 kilometers per day. That strip is maybe 200 kilometers long and 20 kilometers wide, so about 4,000 square kilometers per day in ideal conditions. The total ocean area is 361 million square kilometers. At 4,000 square kilometers per day, one ship would need about 90,250 days, or roughly 247 years of continuous operation to map the entire ocean. Obviously, we have more than one ship. Projects like Seabed 2030 are coordinating multiple vessels and data sources to map the entire ocean floor by 2030. It's an ambitious goal requiring unprecedented international cooperation, but even when we complete the mapping, that's just topography, the shape of the seafloor. Actually exploring those areas, understanding the ecosystems, geology, chemistry, and biology will take far longer. Part 7. What we're missing. So what's actually down there in the unexplored 75 to 80% of the ocean that we haven't examined in detail? New species. Scientists estimate there might be 700,000 to over 1 million marine species in total, and we've identified maybe 250,000 to 300,000. That means potentially 500,000 to 750,000 species we've never seen. The deep ocean is particularly rich in undiscovered life. Every deep-sea expedition discovers new organisms, bizarre fish with transparent heads, giant amphipods, strange worms living near hydrothermal vents, unique microbes that survive in extreme conditions, geological features. We're constantly discovering underwater mountains, volcanic vents, trenches, canyons, and other formations. The mid-ocean ridge system, a chain of underwater volcanoes circling the globe, is longer than any mountain range on land, and we've explored only a fraction of it. Hydrothermal vents, discovered only in 1977, support unique ecosystems based on chemosynthesis rather than photosynthesis. How many more vent fields exist that we haven't found? Mineral resources. The ocean floor contains vast deposits of minerals. Manganese nodules, potato-sized rocks rich in metals, cover large areas of the abyssal plain. Rare earth elements, crucial for modern electronics, exist in seafloor sediments. Massive sulfide deposits near hydrothermal vents contain copper, zinc, gold, and silver. These could be economically valuable, though deep-sea mining raises serious environmental concerns that we're only beginning to understand. Archaeological treasures. An estimated 3 million shipwrecks rest on the ocean floor. Most remain undiscovered. Some are ancient vessels from Greek, Roman, or Phoenician times. Others are more recent. World War II ships, colonial-era merchant vessels, pirate ships. Each tells a story of human history. Some contain valuable cargo. All are archaeological sites that could teach us about past civilizations, trade routes, naval warfare, and maritime technology. Climate insights. The deep ocean plays a crucial role in Earth's climate system. It stores enormous amounts of heat and carbon dioxide, moderating global temperatures. Ocean circulation patterns, like the global conveyor belt, transport heat around the planet, influencing weather and climate. Understanding these processes is vital for predicting climate change, but we don't fully understand deep ocean circulation, carbon sequestration mechanisms, or how climate change is affecting deep-sea ecosystems. Extremophile organisms. Life in the deep ocean has adapted to extreme conditions that would kill most surface organisms. Crushing pressure, no light, near freezing temperatures in most areas, or superheated water near hydrothermal vents. Studying these extremophiles helps us understand the limits of life on Earth and informs our search for life on other worlds. If life can exist in the lightless, crushing depths of Earth's ocean, maybe it can exist in the subsurface oceans of Jupiter's moon, Europa, or Saturn's moon, Enceladus. Bioluminescence and unique adaptations. Deep-sea creatures have evolved remarkable adaptations. Bioluminescence, producing light through chemical reactions, is incredibly common in the deep ocean. Fish use it to attract prey, find mates, confuse predators, or camouflage themselves. Some species have light-producing organs. Others have symbiotic relationships with bioluminescent bacteria. We're still discovering the diversity and mechanisms of bioluminescence. Part 8. We're getting better at this. Despite the enormous challenges, Ocean exploration technology is improving rapidly, and we're making real progress. Autonomous underwater vehicles, AUVs, can now operate independently for months at a time. They follow pre-programmed routes or make decisions autonomously, mapping the seafloor, collecting water samples, recording video, and gathering data without human operators. They're getting cheaper to build and operate, more reliable, and more capable. Some can dive to 6,000 meters or deeper. Fleets of AUVs could survey vast areas more efficiently than crewed expeditions. Improved sonar systems provide much higher resolution than older technology. Multi-beam sonar arrays can map the seafloor in fine detail from surface vessels. Side-scan sonar provides detailed images of the seafloor. These technologies are becoming more affordable and more widely available. Satellite technology helps even though electromagnetic waves don't penetrate water. Satellite altimetry measures the height of the ocean surface with millimeter precision. Underwater mountains create tiny bumps in the surface due to their gravitational pull. Trenches create tiny depressions. By measuring these variations, satellites can create rough maps of seafloor topography from space. This doesn't replace detailed sonar mapping, but it helps identify features worth exploring in detail. Machine learning and AI are revolutionizing how we analyze ocean data. Algorithms can process sonar data faster than humans, automatically identifying features like seamounts, vents, or shipwrecks. AI can analyze video footage from underwater cameras, cataloging species and behaviors. Machine learning models can predict where interesting features might be located based on known examples, helping prioritize exploration efforts. New materials and manufacturing techniques are making deep-sea equipment more robust and affordable. Carbon fiber composites, ceramic pressure housings, and advanced alloys withstand pressure better than traditional materials while weighing less. 3D printing allows for rapid prototyping and custom parts. Advances in battery technology extend the range and endurance of underwater vehicles. International cooperation is increasing. Projects like Seabed 2030, a collaboration between the Nippon Foundation and GEBCO, aims to map the entire ocean floor by 2030. Ocean Census, launched in 2023, aims to discover 100,000 new marine species in the next decade. These initiatives pool resources, share data, and coordinate efforts across nations and institutions. Commercial interest is slowly growing. Companies interested in deep-sea mining are investing in exploration technology. Tech companies are installing undersea cables and need to survey routes. The fishing industry wants better data on ocean ecosystems. While commercial ocean exploration is still limited compared to government and academic efforts, private investment is increasing. Citizen science is even contributing. Projects like Ocean Networks Canada operate cabled observatories on the seafloor, with cameras and sensors streaming data in real time. Anyone can watch the feeds and report interesting observations. Volunteer divers and boaters contribute to mapping efforts using consumer-grade equipment. The ocean's not going anywhere. It'll be there, dark and deep and full of mysteries, waiting for us to finally explore every trench, every vent field, every underwater mountain and canyon. And when we do, what we find will change how we understand our planet, the history of life, and maybe even the possibilities for life beyond Earth. The final frontier isn't just in space, it's also in the ocean, and we're just getting started.